To understand read and write transactions in Aerospike, it's important to know how each piece in the process interacts with the next. Let's explore how the user application interacts with the Aerospike client library, or client, as well as how the client interacts with the server as create, read, update, and delete transactions are processed. Once a client connection to the server has been established, creating a new record starts with the user application providing the namespace, set name, and key to the client with the specific bins and data to be stored within them. The client hashes the set name and key to create a 20-byte digest, from which the partition ID for the new record can be derived. Once the partition ID is defined, using the cluster's partition map, the client is able to send the request in a single hop to the node that will own the master copy. At the server, a new entry in the primary index is created, using the digest along with the storage location, if using storage engine device, and other record metadata. The record is then written to the write block on the node, as well as any nodes that will own a replica, and an acknowledgement of success is sent back to the client. At this point, the data has only been stored in RAM, and relies on the write block to be flushed asynchronously to the device. The write block is a buffer of predetermined size, default 1 megabyte, that write transactions are stored in before being flushed to the device. This streaming write buffer flushes to disk when the next transaction cannot fit in the remaining space and another write block is started. The block will also flush every 1000 milliseconds by default for lower write throughput workloads. For maximum durability, a namespace can be configured with the commit to device option to flush the write block to persistent storage across all replicas synchronously, before success is returned to the client for a write transaction. Reading a record starts a lot like creation. The user application provides the namespace, set name, and key to the client requesting all bins, specific bins, or metadata only for that record. The application may alternatively provide the namespace and digest if the key is not known. The client again hashes the set name and key to derive the digest, and through that, the partition ID, then makes a single hop to the node that owns the master copy, though a node owning a replica may be used depending on policy. At the server, the digest is identified in the primary index of the appropriate record, which is fetched in its entirety, then the requested bins, or metadata only, are returned to the client. Updating a record starts much like the create and read transactions covered earlier. The user application provides the namespace, set name, and key to the client requesting specific bins and data to update or replace the existing record. The client goes through the same hashing process to identify the node and partition for the record. Then at the server, the record is read. The record is updated with the new data and written to the current write block to be sent to a new storage location for the master copy, as well as any nodes with replicas. If the record is being replaced, the read is skipped, and the new record is written to the current write block for the same treatment as the update. Acknowledgement of the update or replace success is sent back to the client, and the original record storage location will be recovered during the defragmentation process. Deleting records starts just like the other transactions. The user application provides the namespace, set name, and key to the client, which then hashes the set name and key to identify the node owning the master copy of the record, making the single hop to the server. At the server, the primary index is deleted on the node, as well as any nodes owning a replica. Applications can make deletes durable, in which case a tombstone entry is written to the device. Durable deletes avoid the possibility of records being resurrected during a cold restart. Acknowledgement of the deletion is sent back to the client, and the record storage location will be recovered through defragmentation. Using a time to live, or TTL, can be useful for data and memory management by allowing record expiration and removal to happen automatically after a set duration. The default TTL in an Aerospike database is to live forever.